Good morning, AP Statistics. We've kind of missed each other the last couple days, so I thought I'd make a video to kind of get us caught up and back on track at least a little bit. I haven't made a big deal about it, but we are now 3/4 of the way through the major units in this class. In fact, the only unit that's left is called inference. And to get started with that, just to kind of give you an example of something that uses inference, I have something behind the desk that you can't see, and I'm going to do something with it. I don't know if you could hear that or not. It's a big pop. And you might infer that I just popped a balloon, and if that's the case, you would be right. Others examples of inference: if I walked by the field house at, let's say, 6 or 7 o'clock on a Friday, and I heard the national anthem being played, I wouldn't even have to walk in there. I would infer that probably a basketball game or a volleyball game was going on, and that would probably be right. A lot of times if I walk into lunch on my way to the teacher's lounge and there's extra long lines, all of a sudden I infer, oh, it's probably turkey and gravy day. I don't know that, but I make that inference based on some evidence that I have and some previous knowledge. And so that's what the basic idea of inference means: to make an educated guess about something without saying everything, but based on some good knowledge. And that's what it means to infer. That's what we're going to do a lot of at this point. We're going to make inferences in a lot more different kind of cases. In fact, most of our inferences will be something like this. When I got on the internet last night, they gave President Trump's approval rating at 41%. That was probably not 41%, because there's no way that they went and asked everybody in the country. In fact, they didn't ask me. So they're making an inference about probably 150 million registered voters based on a smaller sample of that. But they're making an inference. So they're guessing what the whole country feels based on what we call the sample. And you and I have used the term sample before. Maybe another example: if we want to know the average amount of college debt that someone has when they graduates, they don't have to go and ask all of the college graduates. They simply take a sample. And to use those words again too, any number that actually describes the population is called a parameter. So back with the President Trump example, the actual percentage of people that approve of his job as the president, we'll never know that. That's a parameter. And they even use alliteration. So parameters describe the population. When we go take a sample, because most of the time if they want to know the approval rating for the president, they probably only talk to 800, 1,000, maybe 1,200 people. That's a sample, and we've talked a lot about how to take samples. That number is called a statistic. So statistics describe samples, and parameters describe populations. What we really hope is that the statistic we get from our sample is really close to the parameter from the population. So if we go back to the example of college debt, and they find, I looked up last night, they said something like $39,000 is the average debt. They don't know the actual debt for average for college students because they didn't talk to everybody. They hope that that 39,000 statistic that came from their sample is really close to the actual number for the population, but we'll never know that for sure. So again, some alliteration to help you remember those words. And probably the most important thing in this whole chapter is something called a sampling distribution. And I really need you to get down what that term means, what it feels like, and what sampling distributions have to do with parameters and samples and statistics and populations. There's a big connection between those two, and I need you to see what they look like. So I'm going to help you get started. I'm not even going to tell you what a sampling distribution is yet. I'm going to have you build a couple of them. And here's a really easy example to get started with. Let's just say I have a population, and there's only 6 people in this whole population. One person is 1 foot tall, one person's 2 feet tall, one person's 3 feet tall, one person's 4 feet tall, and on and on. There's only 6 people here. Because there's only one of each person, these are equally likely. In fact, you already know the name for distributions even across like that. It starts with a U. I'm going to have you come up with that yourself. But if I wanted to know the average height of people in this population, and for some reason I just don't have the time or resources to talk to all 6 of them, just like back here, we don't have the time or resources to talk to all 150 million American voters, we would take a sample. Now I understand over here, it's not that hard to talk to 6 people, but play along with me. We need to start with really small populations so that I can get across to you how to talk about big populations. So here's the idea. I decide, gosh, I only have time and resources to take a sample of 2 people. And what if, just what if, the sample I happen to get is these 2 people? Now the mean height of the whole population is not that hard to figure out. Because it's symmetric like this, the mean height is actually 3.5. That's not hard to figure out. But what if my sample happens to be these 2 people? Well, I'm going to calculate the average of those 2 as 1.5, and I'm going to put that number right here. Another sample I could possibly get, if I just draw 2 people at random, I could get these 2 people as my sample. I take an average there, and the average of 1 and 3 is 2, so I'm going to put an X here. I'm starting to build a histogram. You can build histograms with X's, you can build them with boxes, it doesn't matter. What we do know is that the height, or the stack, the height of the stack tells you how probable that value was. I'm going to let you finish this one yourself. I do need to let you know, if you get, for some reason, another sample, a mean of 2, you would stack another X on top of it and build it higher. There's another way to do this too. If I had some more time or resources, I could take a sample of size 3. Again, I know a population of only 6 people is not that big to start with. But if I took a sample of size 3, I might get more information. And one of the samples I could take, what if I just happened to get people 1, 2, and 3? Well, I would take the average of that, and the average of 1, 2, and 3 is 2. Well, there's one of my sample means. Another sample mean I could get, if I happen to pull out people 1, 2, and 4, if I take the average of those 3, I get 2 1/3. Well, now I need to make a mark at 2 1/3. What I'd like you to do is finish that one too. And you know how to figure out how many samples there are. And out of a group of 6, there are 6 choose 2 samples of size 2. Down here, there are 6 choose 3 samples of size 3, so you'll know when you're done. And we know we've had problems, sort of keeping track of when you have them all. At least you know how many you're supposed to get. So when you get done, you should have 15 or 20 sometimes numbers in each of these. Again, if you get a duplicate, you stack it on top. Because what I'd like you to do when you get done is sit back and take a look. How does this population compare to this sampling distribution? And how do both of these compare to this sampling distribution? So for tomorrow, I know it's a snow day, but for tomorrow, I need you to have finished questions 1 through 7, which you really were supposed to have done yesterday. And then I'd like you to finish both of these sampling distributions, and then write something. How are these 3 the same, and how are they different? I'll see you tomorrow.